Espaillat, who's going to tell us about the Herschel view of dust evolution in protoplanetary disks.
Thanks. So good afternoon. Before I get started, I want to thank the conference organizers for bringing us all together. I also want to acknowledge my collaborators who were co-eyes on the Herschel proposals that I'll be showing you results from today. So the work that I'll be showing you is related to one of the fundamental questions in astronomy, which is how do planets form? And particularly, how do they form out of disks? So we know that most stars, if not all, were once surrounded by protoplanetary disks, and planets form out of these disks. But what are the details of that process? So we heard a little bit about that earlier today, and we'll hear about it more as we progress in the conference. But the very general idea is that dust grains in these disks are sticking to one another. They're growing into planetesimals, which go into forming planets. And if we want to get a much more detailed understanding of how planet formation occurs in disks, one approach is to look for those disks that display the signatures of planets forming within them. So we can look for the footprints that planets leave behind in disks. And theoretical simulations tell us that as a planet is forming in the disk, it should clear out a hole around itself, leaving behind a footprint in the form of a hole in a disk. And to date, we have detected many of these holes in disks, and we call objects with such holes transitional disks. And by studying these transitional disks, we can start putting constraints on theoretical models of planet formation with these observations. So most disks around young 1 million-year-old T-Tauri stars are full disks, but as Shauna was telling us yesterday, about 10% of disks around young stars have holes and gaps in their dust distribution, the transitional disks. So I'm going to start off with a very brief introduction to the transitional disks, and then I'll move into the Herschel results that I'll be focusing on most of my presentation. And I'll be discussing the detection of water ice in disks with Herschel, and also evidence that we see for lower gas to dust mass ratios in disks. And I'll explain how this can be linked to planet formation in these transitional disks. So here I have the spectral energy distribution, the SED of the transitional disk, GM-Oraigi. The observations are in blue. The emission that you would expect to see for a bare T-Tauri star photosphere is this broken magenta line. And the broken gray line is the emission that you would expect to see for a typical full disk. So this is the median SED of stars with disks in the 1 million-year-old Taurus star-forming region. And you can see that GM-Oraigi has a deficit of mid-infrared emission relative to what you expect to see in a full disk. And that's telling us that the hot dust close to the star has been removed and that we have a hole. But this hole is not completely evacuated of all dust. We see a small near-infrared excess and a strong 10-micron silicon emission feature, which is an indication that there's still some hot sub-micron-sized dust close to the star. And we can put constraints on the parameters of these transitional disks with SED modeling. And Charlie Key told us yesterday about the Paolo D'Alessio's disk models, and those are the models I'll be using for my presentation. These are irradiated accretion disk models, and the best fit model to the SED is this black line, and it consists of an optically thick disk that has a hole. And the outer disk is inwardly truncated at a radius of about 20 AUs, so out to the orbit of about Uranus in our solar system. And we call this inner edge of the disk the wall. It's frontally illuminated by the star, so it emits very strongly in the mid-infrared wavelengths. And we can explain the 10-micron feature and the near-infrared excess with about 10 to negative 10 solar masses of sub-micron size optically thin dust within the hole. Now, at first, many thought that the SED-inferred holes in disks were due to degeneracies in SED modeling, but more and more we're starting to see that there are indeed holes in disks, particularly when we look at sub-millimeter interferometric images. This is some work done by Meredith Hughes for GM-Oraigi, the object I just showed you. These are 860 micron data and 1.3 millimeter data for the object. And in the middle panels, we have synthetic images based on the SED fitting that I showed you in the previous slide. And the residuals between the two are very small. So this is a strong confirmation that there is indeed a hole in the large dust grain population of GM-Oraigi. And of course, much more work will be done to further this with ALMA in the near future. So that's a very brief introduction to transitional disks. Most of what we know about these objects is from their spectral energy distributions, particularly in the mid-infrared and sub-millimeter imaging. And now I want to show you what we can learn about transitional disks when we look in the far-infrared and the sub-millimeter wavelengths. And this gives us access to parts of the disk closer to the midplane, where we are expecting planets to form. So Herschel gives us access to detecting the water ice feature in these disks. Water ice is very important because dust grains that are coated in ice will be stickier and are more likely to grow to larger sizes. So dust grains that are covered in ice can grow to sizes about 100 times larger than dust grains that are not covered in ice. Ice is also important because we think at the snow line, grains grow via condensation onto the grains, and they can grow up to sizes about 10 centimeters or so. And there are several posters on the ice line and disks, and particularly the poster 715 by Ross looks at this condensation onto ice grains. So it's very important to look for ice in disks because if we see ice in disks, we know that that enhances grain growth and possibly planet formation in disks. And we can look for ice at different wavelengths. So here the opacity of ice is the blue line, the yellow line is silicates, the black line is carbon. And we have detected ice in absorption in the mid-infrared with Spitzer IRS, and we've also detected evidence for hot water vapor. The problem is that these short wavelengths, we're looking at the upper layers of the disk. And with Herschel, we're starting to look closer to the midplane. And with Herschel PACS, we can start to see this smaller ice feature in the far infrared wavelengths. And this is work that is being led by Melissa McClure, who's a graduate student at the University of Michigan. And she'll be graduating this spring. And these are three objects: a full disk, a transitional disk, and an outwardly truncated disk. And this gray line here is to guide your eye. So in this bottom disk, we don't see any evidence for ice. But in the transitional disk and in this full disk, we see this triangular shape, which is consistent with where we saw the peak in the ice opacity in the far infrared wavelengths. And we're still working on modeling this transitional disk, but the results for the full disk, GQ loop, have been published. And here we're zooming in on this part of the SED. The IRS data are here. Here are the PACS data. The black line is a disk model with no ice in it. And the gray line is a disk model where 25% of the dust in the disk is ice grains. And so we can reproduce the PACS data reasonably well by assuming that there is some ice in the disk. And the next step in our project is to look for ice and the amounts of ice in the transitional disks versus the full disks. We have 40 disks in our sample. And the goal is to see, do transitional disks in general have more ice than full disks? And can we link this to planet formation, which is causing the holes in these transitional disks? So Herschel also gives us access to measuring dust grain growth and settling in disks because it's looking closer to the midplane at longer wavelengths. So as I said earlier, dust grains in the disk collide with one another, they stick and grow, and the heavier dust grains settle to the disk midplane. So the smaller dust grains, in red here, micron-sized grains, will be well mixed with the gas, which are the gray points. However, when you look at the distribution of millimeter-sized grains and centimeter-sized grains, they'll be more condensed around the midplane at smaller scale heights. And we can actually measure the amount of dust grain growth and settling in disks with SED modeling. So here are simulated spectral energy distributions for disks with different amounts of dust grain growth and settling. The dark gray line, this disk has 100 times more settling than the ones with the in light gray. And the solid lines are disks that have millimeter-sized grains in their midplane. And the broken lines are disk models with centimeter-sized grains in the midplane. And these are the wavelengths that are covered by Herschel PACS in blue and Herschel Spire in green. And you can see that at these wavelengths, we can start to disentangle the models and put some significant constraints on dust grain growth and settling in the disks. And previously, we couldn't do this kind of study. So this is the pre-Herschel SED of GMRIG. It's one of the best studied disks to date. And we have these huge gaps in the SED. And so we can't really put significant constraints. However, this is what the SED looks like if you include the Herschel data. So here are the Herschel PACS data and the Herschel Spire data. So you can see that we have significantly enhanced our wavelength coverage in these regions, and you can see the potential of starting to constrain grain growth and settling in these disks. And in my sample, I have 150 disks. And the goal is to measure dust grain growth and settling in the transitional disks versus the full disks to see if the transitional disks show more grain growth and settling, which would support planet formation occurring in these disks. So these Herschel data finished coming in March, and we're just wrapping up the data reduction for the 150 objects. But I've already started some preliminary modeling, and here are some results that I find for GMRIG. So the solid black line is a pre-Herschel fit to the SED of GMRIG. Before, we did a pretty good job of fitting the SED, but now when we include the Herschel data, the fit isn't as good as it was before. And so there's some extra emission in the far infrared and the short sub-millimeter wavelengths that we're missing. And I can do a better job of reproducing this emission if I increase the mass of the disk. If you increase the mass of the disk, you make it more dense, it's more optically thick, so you can get more emission out at these far infrared and sub-millimeter wavelengths. The problem in this model is that the disk mass is comparable to the stellar mass, and so this is clearly an unphysical disk. But what this could be telling us is that we have lower gas-to-dust mass ratios in the transitional disks. And if we have a lower gas-to-dust mass ratio, we typically assume 100 as the standard. If we have a lower gas-to-dust mass ratio, we can reproduce the same fit, but with a lower disk mass. So the reason this works is because the flux in the millimeter wavelengths is proportional to the mass of the dust. And that's proportional to the inverse of the gas-to-dust mass ratio times the mass of the gas. So if you get an enhancement of dust in the disk, you can get the same flux in the millimeter, but with a lower gas mass. And in the case of GMRIG, with a gas-to-dust mass ratio of about 40, we can reproduce the SED with a reasonable disk mass that is not too very unstable. So a lower gas-to-dust mass ratio in transitional disks is consistent with one of the mechanisms that's been proposed to explain these holes in disks, and that's dust filtration due to planets, which we heard about earlier today in Zoe's talk. So the way that this works is that a planet induces a positive pressure gradient at the wall, and that acts as a filter. Large dust grains are held back in the outer disk, but the small dust grains and gas filter through that wall and go into the innermost disk. And so the distributions of the gas and the small dust are relatively unperturbed. We just see small gaps. But in the large dust distribution, we see a very large hole in the dust distribution, consistent with what we see in millimeter imaging. And so this model could lead to lower gas-to-dust mass ratios because we're depleting the amount of gas in the outer disk while enhancing the amount of dust that's left behind. And further supporting that this could be unique to transitional disks, when we look at the full disks in our sample, we don't see this very strong far-infrared emission. And actually, we can fit the SEDs with a disk model that has a standard gas-to-dust mass ratio of about 100, whereas for GMRIG, we needed a ratio of about 40. And GMRIG isn't the only transitional disk where a lower gas-to-dust mass ratio has been proposed. So these are PAX Oxygen 1 observations by T et al. And based on modeling of this line, they infer that the gas-to-dust distribution in TW Hydra, which we heard about yesterday, is about 30, so comparable to what we see in GMRIG. Now, this isn't a clear-cut case because more recent work looking at the HD line has found that the gas-to-dust mass ratio of TW Hydra is more like 100. So this is still an open area. We're still not sure where the gas-to-dust mass ratios in these disks are. But with the sample of 150 objects that's composed of transitional disks and full disks, I think we can start to make progress in seeing what is the gas-to-dust mass ratio in these transitional disks relative to the full disks. And one possible thing that we might be able to tease out is there a correlation between disk evolution and the evolution of gas-to-dust mass ratios in protoplanetary disks? So it could be that we start out with these full disks with well-mixed dust and gas, and they have standard gas-to-dust mass ratios of about 100. They could be somewhat lower because there's gas accretion onto the star and also photoevaporation, which is dissipating some of the gas in the disk. But once a planet forms in the disk and you can have filtration, you can get significantly lower gas-to-dust mass ratio on the order of tens, so 30 to 40, like we see in TW Hydra, possibly in GMRIG. And then eventually, of course, we expect that the vast majority of the gas in these disks is dissipated, and we end up with debris disks where there's gas is very difficult to detect. They have very small gas-to-dust mass ratios. So stay tuned in the next couple of years as we start to put out the papers from our sample of 150 disks with this Spire data. So in conclusion, this is a very exciting time to be studying transitional disks. We've made a lot of progress in the past with spectral energy distributions, mainly with Spitzer IRS data. And now in the next couple of years, we'll be making more progress with spectral energy distributions looking at the far infrared and the sub-millimeter wavelengths. And also, of course, there's a lot of work to be done with ALMA. And just as evidence of how exciting this field is, these are all of the posters, the few that I could pick out from the titles that are related to transitional disks, and I encourage you to check these out. Thank you very much.
Thank you. We've got time for some questions. Oh, no. Yep.
If I understood correctly your dust to gas mass ratio argument, you still have to start with a full disk initially when the dust to gas ratio is like 100, 1 over 100, which is comparable to the solar mass or so. So is it a problem?
So we're assuming here that the the gas-to-dust mass ratio is lower because of the presence of planet-inducing dust filtration. But of course, you need a higher...
Yes, but this is in a sort of transitional disk phase. But you have to start at still mass ratio of 100 initially. And you said that if you take all the dust mass that you observe, multiply it by a factor of 100, you get something comparable to the stellar mass. So the full disk has to start with a mass which is comparable to the mass of the star. And that probably is a problematic thing,
Yes,
right?
yes, it is. And what's interesting is that these transitional disks, they, as Sean was talking about yesterday, they tend to have the highest mass disks. So it may be that at some point they had to be gravitational unstable, and that would enhance planet formation in these disks. But yes, they should. It seems like currently these are the most massive disks, and they should have, even in earlier stages, been even more massive.
Any other questions? Yep, down the front.
That was really interesting talk. I had a question about the gas-to-dust ratio. You'd expect the gas-to-dust ratio on average to be 30, but wouldn't
Yes.
it be really high at this wall?
Yes.
And still 100 or close to it in the far disk?
So we haven't looked at the radial change of the gas-to-dust mass ratio in the disk. I doubt that having a very high gas-to-dust mass ratio at very small radii close to the wall could reproduce the excess that we see in the far infrared. It needs to be on a more global scale.
I see.
But that is work that I'm planning on doing.
But you do expect, yeah, okay, great.
Any final questions? Okay, well, let's thank Catherine again.